Hi everyone, welcome to the episode number 11. Now, before we move ahead, I just want to give you a quick advice. I have been looking at a lot of comments. Sometimes you find a problem to be difficult. Okay, that doesn't mean that you are not going to learn it. Just watch the video. If you are not able to watch it in 1.5x, slow down the speed, watch it in 1x. Okay, try to understand each and everything that's being going on. I'm drawing the recursion tree. You also try to draw the recursion tree. Okay, then you will be able to understand it much better. And I guarantee if you watch the lecture nicely, 100% you will be able to understand the concept. Why? Because I'm not skipping anything. I will make sure that I'm not skipping anything. So you will get the complete information. It is just that you don't have to hurry up. Okay. For most of the people, it's being so smooth till now. But for few, I was reading the comment section, I found that they were struggling in like maybe a medium level recursion question. So you need to basically take a pen and paper, draw the recursion tree, try to code it by yourself, and you will be able to understand it. That is guaranteed. Okay. One more advice is, whosoever is following this series, after each video, try to summarize whatever you have learned in this video. Okay. And put it in the comment section. So whenever the next time you will come to this video, you will look at the summary and you will be able to understand that okay, these were the points which I noticed when I studied this lecture 1 month ago. Okay, you will be doing a revision, right? So when you will be doing a revision, these notes will be very helpful for you all. So make sure that you summarize the lecture and put it in the comment section. It's a very good habit, and if you follow this till the end, you will be able to master recursion. Okay. Now, in this lecture, we will be looking at combination. So it's a very famous, again, a very famous question, combination. So there's a prerequisite for this lecture. Also, the prerequisite for all the lectures are given in the comment section. Sorry, not in the comment section, in the description. You will find the prerequisites, list of prerequisites in the description. Just go and watch it if you have not watched it. If you remember, if you have watched the lectures, then you don't have to watch them. You can continue with this. Okay. So the prerequisite for combinations is subset. Okay. In the lecture number 7, we generated all the subset. In the lecture number 10, we generated the unique subset. Just go and watch those lectures. You will be able to comfortably understand this particular lecture. Okay. So we are talking about combinations. I hope you remember permutation and combination. We studied this in our high school, and there were certain formula for permutation and combination. So in this question, we will be given certain numbers. Okay. We will be given certain numbers, or maybe we will be given a range. So let us say the range which is given to us is 4. Okay. So this range denotes that we can pick up numbers from 1 to 4. So the possible numbers which we can pick or which we can select are 1, 2, 3 and 4. Okay. So this was the range which is given to us, and that's why we will be able to select numbers from 1 to n, 1 to 4. Okay. Now, how many numbers we want to select? We want to select k numbers. Let's say k is equal to 2. Okay. So you will be given two things. One, the upper range, which will denote that you have all the options from 1 till that range to select from. Okay. Second, the number of elements that you want to select. So now out of 1, 2, 3, 4, you want to select 2 elements. Okay. So one of the possibility could be selecting 1, 2. One of the possibility could be selecting 1, 3. One possibility is selecting 1, 4. Then another possibility is to select 2, 3. Then 2, 4. Then another possibility is 3, 4. So these are the 6 possibilities, right? These are the 6 combinations. Okay. All right. So we need to generate this. So basically we can consider this as we want to generate the subset of size 2. We want to generate a subset of size 2. Okay. All right. So we have already seen that how we generate subsets. So for each element, we have two options, either to consider this into our subset or to ignore it. Okay. We can consider a particular ith element in the subset, or we can skip that element. These are the two options that we have for every element, right? All right. So now again, let us draw the recursion tree. We will see certain improvements that we can do, because while generating subset, we were generating subset of all the sizes, right? We were generating a subset of size 0. and we were generating a subset of size n as well, right? We were generating all the possible subsets. But here there's a boundation. The size of subset should be 2. So when there's a boundation, we can improve the solution a little bit, right? So for example, let us say I already have 2 elements in the subset. I will not go beyond that. I will just stop at that particular point. Okay, there are certain improvements that we can see while drawing the recursion tree. So let me go and draw the recursion tree. I will start with, again, I equal to 0 with an empty subset. Now when I is equal to 0, I am talking about this particular element 1. So two options. One option is to consider it, one option is to skip it. Then again, here I is equal to 2, right? Sorry, I is equal to 1. So when I is equal to 1, I'm talking about this 2. I can ignore it, I can consider it. So let us say I'm considering this 2, so I will get 1 comma 2. If I'm ignoring it, I will be getting 1. Here also, let us say if I'm considering it, I will be getting 2. If I'm ignoring it, I will be getting empty. I is equal to 2 here. So I'm talking about this particular 3. Now from this particular branch, from this particular node, I will not go beyond. Why? Because the size of subset is already 2, right? Okay, so I will not go beyond this. I will stop at this particular point for this particular node. Then let's talk about this node. So here again I have 2 options. One option is to consider the ith element, which is 3, so 1 comma 3, or to ignore 3. If I ignore 3, it will remain 1. Then here also 2 options. One option is to consider it, 2 comma 3. One option is to ignore it, it will remain 2. Here also 2 options. One option to consider it, it will be 3. One option to ignore it, it will still be empty. Okay, then I will be equal to 3 here. All right, when I is equal to 3, we are talking about this 4. So we will not go beyond this particular node. Then here again I have 2 options. One option is to consider, that is 1 comma 4. One option to ignore, it will remain 1. And for this particular node, I will not go beyond. For this particular node, again I have 2 options. One option to consider 4, one option to skip 4. Here also 2 options. One option to consider 4, 3 comma 4. One option to skip 4, it will be 3. Here also 2 options. One option to consider 4, it will be 4. One option to skip 4, it will be empty. So I have 1 comma 2, I have 1 comma 3, I have 1 comma 4, I have 2 comma 3, 2 comma 4, 3 comma 4. So in total 6 combinations I have. So that's how I will be solving this problem. So what are going to be the base conditions here? The base conditions in the subset problem was when I reaches till the end, when I reaches the size of the array. That was the only stopping condition when we were generating subsets, because we were free to generate subsets of all the possible sizes. But here the base conditions are slightly going to change. So we will also consider the size of the subset as the base condition. One base condition obviously will be I, the ith element. Okay, that will remain the base condition. Then one more base condition will be added, and that base condition will be the size of the subset. So if the size of the subset is equal to the given k, we are not going to go beyond that. We will return from there. We will save the answer and return from there. Okay, this is going to be the another base condition. So 2 base condition we have already seen. Now there's one more improvement that we can do here. So here what we are doing, we are trying to generate a subset of size 2, right? And we are avoiding ourselves to go in the direction where the size of subset is exceeding 2, and that is saving us some time. Okay, there's another improvement that we can do. Just pause the video, think of it. What else can we do? Is there any way we can avoid going to these particular nodes where the size of subset is 0 or 1? We can even avoid it, right? We can avoid it from here itself. Then why are you even going to that side? If you are going to that side, you will not be getting the subsets of size 2. So you can even avoid going to these sides, right? So for that, there should be another condition. Just think of it. Maybe you can pause the video, take a pen and paper, try to think of the approach, and then you can code it along with me. Okay, so now let us jump to the coding part. There itself I will show you what condition can we put. Basically, what is the third base condition that I can put to even improve the complexity. Okay, by putting these base conditions, we are just improving the complexities, right? We can even put only one base condition, that is of I. When let's say when we were generating subsets, right, we had only one base condition. When I reaches the end, then we were stopping, right? In that case, we ended up generating all the possible subsets, right? 2 raised to the power n. But here we don't need all the possible subsets. We don't need all the possible subsets, but our answer lie within all the possible subsets only. So that's why we can generate all the possible subsets for sure. Okay, I will show you with the help of the code itself. So here's the code. So we are given n as the upper bound, as I told you, and we have numbers from 1 to n. Okay, and we need to generate the subset of size k. All right. So let us start solving this. First of all, I will be creating a helper function, void help. In this I am taking I. This I denotes the current number on which I am currently standing on. Then I will have the upper bound n. Then I will have k. Then I will have subset vector of int subset. Then I shall also have a vector of int answer. If you remember these steps, then it's fine. If you don't remember, just go to the lecture number 7 and see what all things did we discuss there. So everything has been discussed. We are writing exactly the same solution, subset. Okay. So for every element, I have two options. One option is to consider this, to take this element. So take the ith element. Okay. If I'm taking the ith element, I should put it inside the subset. Subset dot push back the ith element, okay, and then ask recursion to do the remaining task. What is the remaining task? From I+1, do the remaining task n, comma. Now how many elements do I need? Now I need k minus 1 elements, right? Because one element has already been taken, so I need k minus 1 elements. That's why I'm passing k minus 1 here, okay? So k is the total number of elements that I want in the subset, right? So initially it was given to me as k. Now I picked up one of the element. Here I am selecting one of the element, right? That's why it is k minus 1. I will ask recursion to do the remaining task from I+1, and I will also pass k minus 1 because one element I have already selected. Now recursion have to do the remaining task with only k minus 1 elements. Recursion only have to select k minus 1 elements, right? That's why I'm passing k minus 1 over here. Then subset, comma, answer. Okay. Now ignore or skip the ith element. If I want to skip the ith element, first of all I will have to pop it out because I have already inserted it in the line number 4, so I need to pop it out, pop back. So I'm popping this out. Now I am not considering the ith element. I will ask recursion to do the remaining task from I+1, but again I will be passing k because I'm not selecting any element, right? So recursion have to do the remaining task and recursion have to select k elements. All right. Subset and answer. So this is it. Now the base condition would be, I'm just putting one of the base condition as of now. Later on we will include two more base conditions that we talked about. So first of all, if I is greater than equal to n, not equal to, basically equal to is considered, right? Equal to is acceptable. So only if I is greater than n, then only we are going to stop. We are going to return. But before returning, we should also save the subsets which are of size k, right? We should also save the subset which are of the size k. K is given to us here, right? Or we can say, because we are reducing k, right? We keep reducing k. So we should also save the subset if k is equal to 0. So because we are every time we are picking up an element, we are reducing k, so k will become 0 at the end, right? K will become 0. It will go to negative value as well. K will go to negative side as well, but we have to ignore the negative side. Why will it go to the negative side? Because we have selected more number of elements than what the question wants us to select, right? Let us say the question wants us to select 4 elements, right? And if we selected 5 elements, because there's no restriction as to how many elements I want to select, right? There is no restriction. So that's why I will end up generating all the possible subsets, and that subset could be smaller than what we want, or it could be larger than what we want. When the subset is smaller than what we want, this k will be positive. When the subset is larger than what we want, this k will be negative. and if the subset is exactly what we want, the size of subset is exactly what we want, then this k will be equal to 0. That's why I'm saving the answer here. Answer dot push back the subset. Okay, this will generate the answers, right? Then I will return from here. Now let me create a vector of int subset and a vector of int answer. Okay, and let me call this function help. Initially passing I as 1 because we can consider all the elements from 1 to n, then k, then subset, then answer, and that's it. After this we shall return the answer from here. Let me see how they want the output to be. So input format is this: output for each test case print all the possible combinations in each line. Let us run this. Let us see if we are getting correct answer. Yes, we are getting correct answer. Let me submit this. Hopefully we will be able to submit this. Although we have not improved the solution is 2 raised to the power n because we are constructing the entire recursion tree. We are going from every node, we are going to the deepest level. Okay, but as I told you, there could be a slight improvement that we can do. What is that slight improvement? So let us say I have already selected k number of elements. Okay, so I can put a condition here. I can put a condition over here. If k is equal to 0, then stop. No need to go further. Return from here. Save the answer, return from here. So if k is equal to 0, just save your answer over here and return. Bye bye. Okay. Now this will save us from having subsets of larger sizes. Okay, this will save us from having subsets of larger sizes. Done. When I is greater than n, when I is going beyond the boundaries, then simply return. Simply return. Now you don't have to save the answer because you have already saved the answer at the first base condition. All right. So this is a slight improvement that we did over here. We basically saved ourselves from going to the side where the size of the subsets were increasing because we don't need to go to that side. Okay, we don't need to go to that side. There's another improvement that we can do. Sometimes it might be possible that I keep skipping elements. I keep on skipping elements, and let's say I have a subset of a certain size, and I know that I have only few elements remaining now. Even if I consider all those elements inside, still I will not be able to generate the required subset. Okay, so for example, let us again go to the board. For example, let us say I want to generate a subset. This k is given as 10. This k is given as 10 to us. I want to generate subsets of size 10, right? Now, let's say 20 elements are given to me. 20 elements are given to me. I kept on skipping elements. One by one, I kept on skipping elements, and I reached to, let's say 11. Okay, I reached to 11. Now I have to take a decision whether I should take 11 or not take it. Okay, so here I will be only able to take 11. I have to take 11. There's no way I can skip it. If I skip 11, after 11 what will be there? 12 till 20. So only 9 elements will be there. 12 till 20, 12, 13, 14, 15, 16, 17, 18, 19, 20. 9 elements will be there. So if I skip 11, even if I pick all the elements after 11, I will still be not able to generate a subset of size 10. That's why I cannot go in that direction. Okay. So let's say if I'm standing at 11, and till now I have not picked up anything. Okay. Till now I have not picked up anything. All right. So I will have to select 11. There is no other choice. Okay. Normally what all choices do I have? One choice is to skip 11. One choice is to select 11. Right. So if I select 11, I can go in one direction. If I skip 11, I will go in another direction. But here, the another direction of skipping 11 is not allowed. Why? Because our subset that we have generated till now is very small. And even if I skip 11 and even if I added all the elements which are after 11, I will not be able to generate the required size subset. That's why I should stop going to that direction. And it will give us a very good advantage. This tree, these kind of things will be removed. These kind of things will be removed from here. Okay, like skipping here and skipping over here, these kind of things will be removed, and it will still save us a lot of time. So basically we did two improvements. One improvement, don't exceed the size k. Okay, don't take more than k number of elements in the subset. This was the one direction. Okay, other direction was don't take so less elements in the subset. So we saved, we basically what do we say, bounded it. We bounded our solution. These are called the boundations. So now instead of 2 raised to the power n, it will be much less than 2 raised to the power n, because the tree will be thinner. Okay, the tree will be shorter, it will be compact, number of nodes will be less in the tree. This is how you improve the solutions, and this is how you discuss it in the interviews, right? So what did you do? One thing, you did not allow more number of elements than the required element. Second thing, you did not allow very less number of elements than the required elements, right? So that's why you bounded the solution. That's why the number of nodes reduced. That's why the time complexity, I would not say is reduced, because in the worst case the complexity could be 2 raised to the power n, but the time is reduced, the run time is reduced. Okay, you will see it will help us in the run time. The solution will be much faster, although the complexity wise it will be same, because complexity is in the worst case, right? But in terms of time it will be much better. Then yeah, talking about the time complexity, it will be 2 raised to the power n, worst case. But talking about the space complexity, the height of the tree, the height of the tree will be equal to n, right? That will be the space complexity required. So big of n, space complexity. Time complexity is 2 raised to the power n. And if you talk about the space complexity of the answer that we are returning, we are also returning an answer, right? That's a very huge thing. It contains basically all the combinations. So we have to talk about it separately to the interviewer. Okay, so to the interviewer you will say that okay, recursion is giving us this much space complexity and the answer that we generated is giving us this much space complexity. So the total space complexity is the addition of both. That's what you have to explain to the interviewer. You have to explain it separately. Okay, all right. So now we have a better understanding of how we can avoid going to the size where the size of the going to the side where the size of the subset is increasing so much. So we have already added that condition. Now talking about the other condition where the size of the subset is very less and we cannot afford skipping the element, right? So for that k is the required remaining elements, right? K is the required elements that we want. Okay, and n minus I plus 1 will give us that remaining elements. These are the remaining elements, these are the required elements. So just in case the remaining elements are less than the required elements, in this case we should return. It basically means that we are in the wrong direction. Okay, we are in the wrong direction. Now the remaining elements are smaller than the required elements, so we are definitely in the wrong direction. We should return from here. There is no point going any further down in this direction. We are absolutely in the wrong direction. Remaining elements are less than required elements, so return. So that's what I'm going to include over here. One more condition, if the remaining elements k, sorry, if the required element k are greater than the remaining element, which remaining elements are n minus I minus 1. So in that case, sorry, plus 1. In that case, return, right? So let us see if it gives us the correct answer. Yeah, it is giving us the correct answer. Let us submit this. And it got accepted. So these are the improvements that we can do in the recursion problems, in the backtracking problems. These are certain kind of improvements that we can do. Okay, so if you just think peacefully, these improvements are very easy to do, right? These are very basic things. Okay, first of all, what did we do in this lecture? We basically tried to generate all the possible subsets. Now we don't want all the possible subsets, that's why we bounded our solution. We bounded it from the left side and from the right side. Basically we basically stopped it from going to the direction when the size of the subset is so large, and we stopped it from going to the direction when size of the subset is so small. That's how we improved it, right? So this is it. Make sure that you take a pen and paper. Please try to dry run by yourself. Write down the entire solution. Then only you will be able to digest all these things. And once you digest all these things, right, everything in recursion, everything in dynamic programming will become very simple for you guys. So please, Give it time, give it proper time to digest. Take a pen and paper, not only for this lecture, even if you are not able to understand the previous lectures, make sure that you do the same thing. Summary, try to understand the lecture, write the summary, take a pen and paper, try to learn thing. Okay, try to draw the recursion tree by yourself. This is how we learn. All right, so let us meet in the next episode. In the next episode we will be doing another problem that will be combination sum. Let me show you the problem statement, or you can find the link in the description. You will find link in the description as a homework problem, so you can try it by yourself. In the next lecture we will try to solve it together. Okay, bye bye, take care.